start. All right. Good morning, everybody. I'm in San Francisco today, so sorry that we can't make it in person. Obviously, this is the first seminar of this semester, and we are seeing increasing more people actually, including some data science master students who are going to attend this seminar more in this semester. So it's my great pleasure to introduce Professor Tianxi Li in School of Stats, UMN. So Tianxi joined us last fall. Before this, he spent 5 years in University of Virginia, Department of Stats. And Tianxi's research is mostly in statistical machine learning and statistical learning on complicated networks, especially. So Tianxi got his PhD in stats in University of Michigan, and his bachelor degree in, is it Georgia University, Tianxi?
Yeah.
Oh, yeah, okay. All right, Tianxi, is your floor. Go ahead.
Okay, thank you very much for the introduction, and thank you for the invitation.
Sure.
Yeah. Okay, so it's great pleasure to talk and introduce my work to everyone, all the audience here. All right. Good morning. So my topic today is specifically about modeling complex networks by using nonparametric inference. We could talk about how to do this one for single networks and how to really make inference across different networks. So as a starting point, I want to introduce, generally speaking, what we mean by network data. So typically we use networks to really represent relations or interactions between units in a complex system. So typically when we talk about the relations, this could be how different units are interacting with each other, and we represent such interactions as the edges in the network. And then each unit in the system is represented by a node. The network data could be directly observed in many situations. If you think about social networks, internet, traffic systems, airline systems, in all of these situations, essentially what you directly observe was the network. All right. But in some other situations, maybe we don't really directly observe the network itself. What we observe could be some other type of information. Then we would construct the network by using a certain type of transformation or processing of the available information. One example in this situation is the gene co-expression networks. In this situation, we typically observe the multivariate data as gene expressions. And then we use certain type of either graphical model or WGCA, all of this kind of complicated processing step to construct a network from this multivariate data. And from that perspective, you can see actually most of the biological networks are inferred networks, right? Just other example includes, say, when we talk about brain networks, how different components of brain are co-functioning together from fMRI data, and how the disease spread over, between different people in epidemiology. In all the situations, the networks are mostly inferred. So here is one example. This is the citation network between about, if I believe, if I'm correct, this is between 3,000, about 3,000 statisticians. Each node in the network is a statistician, and two persons are connected in this network if they ever cite each other in their publications. Right? This was actually based on about 10 years publication data on in 4 prestigious journals in statistics. All right. So for another example, here, just for to this talk, I also just include this data example. This is actually the hiring relation between computer science departments. All right. So in this network, each individual node is a computer science department in North America, either in Canada or in the US. This data set was actually collected by Aaron Closet and his team a few years ago. So two departments connect. They say if Department A hires some of the PhD graduate from Department B as their faculty member, so if in that situation, you would have one connection, directly edge from Department B to Department A. All right, so this would be the typical data structure we have in our analysis. And in particular, mathematically, we usually represent a network of n nodes by an n by n adjacency matrix, let's denoted by the A matrix, such that Aij, this matrix on tree, is 1 if and only if there's snatch from node I to node J. Okay. More generally, of course, edges could have weights, could have signs, right? In that situation, we just use, say, we would cite the value of Aij to be the edge weight, including the signs, right? So then the A matrix will be real valued. If we happen to have undirected graph, that means there's no difference between two different directions, and we don't distinguish directions, then intrinsically A is a symmetric matrix. And typically, maybe we're not so interested in many situations, we're not so interested in self loops. So we would just always force the diagonal of A to be 0, right? That means we actually ignore all of the self loops from a node to itself. So in this talk, we will focus on undirected and unweighted networks, all right, just for simplicity. But the methods we introduce could be generalized to weighted networks as well. And we have some version of that. So specifically, we want to talk about statistical modeling analysis with some nonparametric flavor in it. I will introduce specific problems. The first one is about personalizing network data from its raw format. In that situation, we actually introduce a so-called call periphery structure, and we would identify which component of this network is specifically informative for downstream analysis. In the second step, second section, we talk about some, single network learning method with adaptivity. By using the ensemble learning idea, we're able to effectively learn the network structure, network models very efficiently without a specific model, parametric model exception. In the third one, I will talk about using subsampling inference to make inference across multiple networks. All right. So generally speaking, the advantage of using nonparametric methods lies in their generality. Whereas typically, under the nonparametric framework, we have certain type of model-free components in the method. So it could be pretty general. And all tools we introduced today have theoretical guarantees from statistical theory, but that won't be our focus today. We will focus on the high-level ideas and applications. All right, that's the agenda today. Questions so far? All right, so let's start from the first section. So the high-level point that just the motivation of learning the structure of network is really because understanding the specific structure tend to give us insights about the underlying interaction mechanism or relationship, right? So we actually need some probabilistic framework typically to deal with the noisy nature of the data set. So here is one, I would say, arguably one of the most general or widely used frameworks called inhomogeneous Erdős-Rényi framework. So under this framework, we assume that given some unknown probability matrix P, which takes value between 0 and 1 as n by n matrix, each Aij is generated by a Bernoulli random variable with probability Pij independently. And that just actually means if you take the expectation of A, that gives you the probability matrix P. All right. So the P could be random. Sometimes we use some random model for P to introduce. We have some dependence between edges, but the basic structure is conditioning on P, then A is generated independently. Okay. So the modeling procedure or the network analysis procedure is we observe data as A, and we try to estimate the interesting structure of A by recovering P. All right, just very simple procedure. So at a high level point of view, this is just basic, procedure from data to structure, where the data could be pretty noisy and, not so nice, but we try to find the nice structure from it. But that is actually not really what we typically have as a high level picture. Because what we observe in practice is we will try to model a network by using specific interesting structures. It turns out that the informative structure is only part of the network data, right? It is something like we have this broad view, just a very large data set, but only a subset of it gives you the needed noisy version of the structure. Therefore, in this situation, if we blindly model the raw network, that would result in some very poor performance in accuracy, in prediction errors, and also in the interpretability. All right. This can be seen as a model specific misspecification problem in some sense, right? Because if we treat this smelling phase, as the key structure we want to learn by our model, and then we have all of the data set in the model, and of course, it seems like we are misspecifying the model. But actually, in our paper, of course, we won't really give the details here. We have shown that this is not really the only reason. Because even if you have a specified model that could automatically incorporate the additional noises, it could still hurt your performance for various reasons. All right, so the basic thing is we hope to get a way to process our raw data set such that we can identify the component of interesting structures, and then we could focus on that interesting structures by removing all of the non-informative structures. So that is a high-level point of view. All right, so specifically, we want to assume model for interesting core plus uninteresting periphery. So that is one of the core periphery structure we want to decompose our network into. So specifically, our model is, let's assume there's a partition of all of the nodes 1 to n into a core set C and a periphery set P. All right, and then we hope that the core set C gives us the interesting structure, right? That is something we might be interested in modeling. We might want to understand the corresponding mechanism. All right, and the P structure is uninteresting. We don't really care about it. Usually, we are not interested in learning what happened there, right? However, what is an interesting structure? It actually depends on the downstream task, which is usually unknown, right? So we are trying to define a general data processing procedure. So we don't really want to constrain ourselves to one specific downstream task. That could be very restrictive. We hope that we provide a procedure where whenever you want to analyze the network data, you could consider this one as a pre-processing tool, right? So we cannot really define what could be interesting for the downstream task. However, it's usually easier to define what could be uninteresting for downstream task. So from our observation, all right, so usually the uninteresting structure for analysis could be something like this: the uniform connection structure, or the original early training random network model. So essentially, for the uninteresting structures, we assume that, okay, all of the connections between the periphery nodes with other nodes are just established purely randomly. That just by the same probability row, okay? There's no pattern at all. Everything is just flat, just uniform. There's nothing happening there. Okay, usually we do not really see an application where people are interested in learning this pure uniform structure. This can be seen as a pretty noisy and uninteresting part. There could be a few other situations where people might want to exclude another type of interesting structure. I call this the configuration type of structure. That means the connection probability between node A and node J, which is this Pij, it is in proportion to the degree of A, or the popularity of A times the popularity of J. All right, so why this is not interesting? Because typically when we call a network a complex network, we're essentially saying that you cannot really understand the structure very well by looking at single units. All right, but if you think about this structure, that means if I focus on the single unit, I know the single unit popularity Di, or the single unit of Dj. All right, if I know the single units, I could already fully model the network structure, right? That means it is not uniform structure, but it's not interesting because there's no complexity in the structure. So in some situations, this is not really the interesting part people want to model. And therefore, we try to find some way to exclude such structures from the network without assuming what could be the interesting in the core structure. All right, so essentially we're assuming the core structure can be any structure that is not periphery. All right, so this is our assumption. Then let's think about how to remove those uninteresting nodes. Okay, so I would just only talk about the very intuitive high-level idea in the ideal situation. Let's assume right now we observe P, right? Just in practice, of course, we don't, but let's assume we observe P. And let's assume that the first half of the nodes, in this situation, we won't have two nodes in this matrix. Let's assume the first two nodes are really interesting cores, and the other nodes are really, the periphery. And we assume we're talking about the ER periphery for the moment. So this would be the P matrix, what P matrix looks like. The core part, it could take any pattern. We don't really assume anything about it. But then it can be seen as a very simple idea to remove that uninteresting structure is we can remove the row average from each row, right? So we calculate the average of each row and we take the average from all of the rows. And you can see that if we do that, because of the ER structure, at least for the row 3 and row 4, we would remove all the row and they become 0. All right, and these correspond to the periphery rows. The core rows are always non-zero according to our model assumptions because they are not uniformly set up, right? That is the definition for the core. So whatever you do there, they won't be 0. So we do not really need any additional assumptions about the core structure. By directly looking at this pattern, we can already separate the periphery structure from the core structure by looking at the row norms after the centering step. All right, so that is really the basic idea for our algorithm, which is called spectral filtering. In practice, of course, we also have to consider what could happen in the configuration time model. And in that situation, we need a little bit more, complicated formulation. But essentially, at a high-level view, we actually introduce one additional degree correction step. We first do the degree correction along the columns, and then we do the row centering step. And then we can still identify all of the periphery structure. And of course, we observe A rather than P. A is no longer perfect as P. So we actually have to introduce some statistical denoising step before applying the previous procedure. And that gives us our practical algorithm for doing this. All right. And again, we won't really talk about the technical details for that. All right. So in this, at the high level view, this model gives the model free for the core component, right? And it turns out that this algorithm can be computationally very efficient. And this is also important because we try to use this one as a data processing step, right? Just that means you have raw data. The raw data could be at very large scale, so it has to be very fast. And theoretically, of course, as I mentioned, it could provide very strong and convenient theoretical guarantees. Now let's look at some example, just what could be done by using this. So again, this is the citation network I introduced a few minutes ago. Oh, okay. So this is actually, okay, about 2,000 papers, average degree about 5, which is a very sparse network. This data set was originally analyzed by a previous paper. They actually used some K-call algorithm to process the data such that they could extract a subset of data as a core structure so that they could just apply the analysis on the subset of the data. So the downstream path in this situation is we try to find some meaningful hierarchical communities of papers. So what do we mean by hierarchical communities? So communities are essentially a clustering structure in networks, right? So in community structure, we hope that we could group nodes with similar connection patterns together as homogeneous local components. And in addition to that, we also hope to have this hierarchical relation between communities, right? This is something like the hierarchical clustering, problem, but the basic intuition is using the hierarchical relation, it gives you the closeness between different communities, right? So generally speaking, it is more interpretable. And also, in practice, it could give you better performance if you have a large number of communities, because essentially you're really introducing some informative structure, which could help you to control the potential noise in estimating the clusters. All right. And then we could also aggregate the small communities by mega communities. For example, if this is our hierarchical tree, we could group this, small communities at the end together and treat the whole thing as a mega community. Again, sometimes that could be pretty interpretable, as we will see very soon. All right, so a fast algorithm of doing that one with theoretical guarantee was actually proposed in our previous paper. And that was really the algorithm we used. And so here we want to introduce, we'll compare a few different core extraction methods, the K-core algorithm from the previous one, and this very intuitive one by Zhang and Newman, just a few other papers like PageRank, by eigencentrality, all of these kind of things. And for fair comparison, we would constrain all of the core sets to be extracted using exactly the same number to match the previous work. So that could be a fair comparison. And after the core extraction, we apply the HC algorithm to find the hierarchical communities. And then we want to evaluate whether, we could do a good job by observing some interesting structure there. All right. Then how to evaluate the performance? So our evaluation is actually based on a separate text data, right? The basic idea is we could get some hierarchical similarity between communities available from the algorithm. And this similarity is purely based on the network structure. In addition to that, we actually have the word frequency vector for all of the paper's abstracts. And then we could also calculate the textual similarity between the communities, right? That is actually purely based on the text data. So we want to compare that whether the hierarchy similarity from the network and the textual similarity, they match with each other. Because if we can do that, that actually means, the hierarchical structure we observe from next structure happen to match the additional information from their research topics, research interests. And that is some intuitive idea about why that could be a reasonable evaluation criteria. And we use the Spearman's correlation to calculate between the similarities as our final metric. So here is the summary of the result. Just so you can see that if you use our processing method by identifying exactly the same number of cores, the corresponding hierarchical similarity is much better compared to all the other situations using the other methods. That just means that by using this data processing step, we happen to extract a very, very interpretable structure that could match or interpret it as the research topic community. And indeed, the left figure gives you the corresponding hierarchical structure between the different communities and their interpretations. And this is actually very interpretable, right? For example, if you really look at the first two category, the first one is hierarchical dimensional, high dimensional statistics with learning methodology and high dimensional statistics with theory, right? They are very closely related communities, and they are also closely related to the high dimensional time series and also machine learning method. This can be seen as a group. Also, for example, multiple testing or inference community is very closely related to neuroimaging studies, because in a lot of neuroimaging studies, you actually have to do a lot of tests such that it involves a lot of multiple testing control. All right, so generally speaking, it gives very, very intuitive view of the data structure there. All right, so in summary, for this part, we introduced a new core periphery model with general core structure and uninteresting periphery nodes. The good thing about it is you don't really have to assume anything about the core structure except that it is not the periphery. The algorithm can be computationally efficient, and if you want to try it, we have the R package implementing the whole algorithm available online. All right, questions so far?
Yeah, I have a quick practicality question here. So if you apply this to a graph, how do you determine how many of the nodes you actually remove?
That's a really great question. Yes. We have several recommendations in our paper. Either you can use some theoretical threshold, just defined by our paper, just with directly connect with our theory. And so, of course, you need to assume a specific, the previous inhomogeneous early training model to make it work, but it works very well if that is a reasonable assumption. Alternatively, you can use some clustering algorithm, say, after calculating all of the rows norms, and you just cluster, them into two groups. Or if you could observe two model plot in their histogram, you can also set a threshold there. And in a few other situations, you can just basically, sometimes you have additional information, right? Sometimes you just know that how many nodes I want to handle in my next downstream task. That could also be a way to find the cut.
Okay, okay.
Yeah. Thank you for the question. Anything else? All right, so let's move on. So now, let's really specifically talk about how to effectively model the network. Recall our previous setup. We assume there is an underlying matrix P, such that just given the P, you generate the A entries by sampling Bernoulli random variables, and such that EA, the expectation, equals this P. Okay, and of course, if you really want to get some interesting modeling performance, you want to assume different structures. There could be many different available options. You could assume there could be community structures, there could be latent space, smooth embedding, all of these kind of things. Or even the most general situation is you just assume this is a nonparametric graphon model that is essentially the assuming some underlying function, which may or may not be continuous or smooth, but this is really the most general framework if you assume just only exchangeable structure between the nodes, right? Just a lot of options in statistics, but there are so many factors to consider if you want to conduct the modeling effectively, right? What could be the reasonable structure assumption? And you have to think about just, I want to handle the network sparsity, because the real world networks can be very sparse. That means, if you really look at the Chesney matrix, it's a very sparse matrix with limited information. There could be a very heavy heterogeneity there, right? Just some of the nodes are very popular with so many connections, but most of the other nodes only have a very limited number of connections. And the size of network can also give you the trouble, because intrinsically, you're handling a matrix. So if you have 1,000 nodes, that will be 1,000 by 1,000 matrix. If you have 1 million nodes, that will be 1 million by 1 million matrix. And you need to take advantage of the sparsity for computation, but still it could be very heavy in many situations. So you also have to take consideration the computational bottleneck, right? There's so many different factors impacting the real world performance of the modeling procedure. So the decision making is actually pretty non-trivial. And so for this task, we try to find, in some sense, an off-the-shelf network modeling strategy such that it could be general and flexible, that just you do not really have to assume too much about your structure, and could be reasonably computationally efficient. And it's almost tuning free with some theoretical guarantees in under certain circumstances. But that is actually the original motivation to design this procedure. It may not be the most ideal method to use if you know a lot of information about your network structure. But say, if you know nothing, you want to start with some reasonable analysis, we hope this could be the first two you could consider, right? Because it just gives you pretty reasonable performance in almost all the situations. That is actually the advantage. Intuitively, we might have a set of possible models or methods available to recover the network structure, right? Let's assume that we have F1, FM, we have different models, algorithm to estimate. Oh, sorry, this is my typo. I should use this. I should not use R. It should be P to be consistent with our previous notation. So let's just take this RSP. Okay, sorry about that. So if we have M different algorithms to recover the potential structure, then what would be the best method to use among the M without knowing which one is the best? right? So can we do even better than the best single one out of the M options, right? Those are really the basic question we want to ask. So here is really the idea of the procedure we design. Let's assume this is our GCC matrix. You can see this is a binary matrix with some of the entries being 0 and the others are 1. So we would randomly hold out a proportion P of the node pairs to be our validation set omega, and the remaining entries would be the training data, right? So I label the validation set by red, and the other entries are still black. All right, so now we hold out the validation data, and we only focus on the training data. And this becomes an incomplete network with missing entries, right? And then we try to fit the candidate models on this training data A omega C, right? All of the black entries remaining here. And we generate the corresponding individual estimators following the M algorithms. Okay, and how to do that, by the way? It really depends on specific algorithm you want to use. If you want, you can just try to apply some matrix completion procedure before fitting the model. Some of the other methods naturally could handle partial networks, and then you can directly fit them out. But anyway, according to the M options, you generate the M estimators. And then in the next step, you calculate some combination coefficient by solving this non-negative least square problem using the information from the validation data. Okay, so A omega is a validation entry. That will be the red part. Okay, then we just try to use this M estimator, taking a linear combination of them, and we constrain all of the linear coefficients to be non-negative. We solve this least square problem, and we would create the corresponding non-negative linear coefficient and use the coefficients to combine all of the information. And that would be the final estimator. We call this procedure non-negative linear mixing. This one can be seen as an ensemble learning method. Essentially, just you have individual models or individual algorithms. They can be treated as your weak learners in the procedure. And then in the second step, we just try to aggregate all of the information from the individual ones by using a specific procedure. All right, and under the inhomogeneous Erdős-Rényi framework, as we introduced before, this procedure comes with very, very strong theoretical guarantee. We can show that automatically it always beats the best individual model out of your M candidates. Okay, so you do not really have to know which one is best, but doing this one, you could always beat the best one. And more importantly, you could actually match the optimal performance line, which lies on the convex cone of the M model spaces. All right, just that is a little bit technical, but just roughly speaking, you can achieve more than just the best single model. But more importantly, notice that this aggregation procedure, it does not really rely on the inhomogeneous Erdős-Rényi framework. Even if you don't really have a model for the P matrix, you just have an algorithm to predict some of the entries, the missing entries at the red validation data. You can still achieve this one. You can still apply this procedure to do all of the model fitting procedures there on the data set. So that's why it could be a very general procedure. So therefore, that just actually gives us the insight about just how to just generally handle a network. And the natural question is, now here we try to solve the nonlinear least square problem, right? We are using a linear combination of the M individual estimators. So why not consider a more complicated procedure? Just how about use some more specific, say, using deep learning models, using other methods like boosting, like random forest, or the tree-based methods, just essentially in some complicated procedure to come up with a better combination. And our theoretical result actually shows that that is actually not a good idea. You may not really gain any efficiency or accuracy by doing that. This is actually because of the network sparsity in practice. Because as I mentioned, in practice, network can be very sparse. And that means they only provide a very limited information. And meanwhile, the observation can be highly noisy. And because of that situation, it turns out that the aggregation step may not be able to handle more complicated model. If you just move beyond this constrained non-negative least square, even if you go to just general least square, the linear combination, it could result in some overfitting issue. So at the end, it may not really give you a better performance. And as we'll just demonstrate this one empirically very soon. So anyway,
Tianxi, a quick question here. So the cognitive models, do you have some minimal requirements on them? I mean, I'm thinking, I mean, if I think about like a boosting kind of algorithm, right? You can't combine models that are worse than random, right? Because that's going to pollute the whole performance, I think. So here, do you have to make that kind of assumption, or it can be anything?
That's a very good question. Yes, we essentially have to assume that the algorithm is basically reasonable. That means it should be better than just purely random guessing.
I see. Okay.
So, but that sometimes that actually depends on your model fitting procedure. We are essentially assuming that the model fitting procedure is reasonable. Maybe your model is not reasonable, but when you fit the model on the data, at least the model fitting procedure should do a reasonably good job, such that you are not really learning just purely noise. Just even if you have an oversimplified model, which does not really capture the complexity of the network, at least it should give you the best, a good performance within the current expressiveness of your model. So you cannot really, my understanding is you cannot really do the adversary training for this framework so far.
I see. Yeah, that makes sense. Yes. Thank you.
That's very, very, very great question. It's very insightful.
Yeah.
So, okay. So let's just talk about literally evaluation. I think just, it happens that just at the same time when we actually work on that paper, there's one paper coming out on, I believe it's either PNAS or Nature Communication, from this computer scientist group. They actually, they evaluated more than 80 link prediction methods in three categories. They talk about some topological algorithms. They talk about network, statistical network models, and also they apply some embedding. I believe some of them are just based on deep learning strategies, GNN things, kind of just embedding type of procedures for link prediction. Link prediction is just a procedure where we hold out some of the network links and we try to make prediction, on the missing links. So then they evaluate all of this performance on more than 500 real-world networks from 6 domains. Biology, econ, information, social, technology, and transportation. And their conclusion is there's no super bullet, no free lunch, right? That is actually expected, right? That is something that the principle we typically believe in. But their proposed solution is the so-called optimal link prediction, OLP. So they show that by using this one, you can empirically achieve not always optimal, but close to optimal performance across all the domains compared to all the individual methods. All right, so that is actually what they have proposed. And it turns out that if you ignore some minor details, the OLP procedure can be seen as a mixing procedure where in this combination procedure, you use random forest to calculate, how to combine the individual estimators. All right. So from this perspective, you can treat this our non-negative linear mixing as a brother or sibling from this OLP in some sense. But we want to do some conceptual comparison between these two options. In OLP, you actually have to fit a random forest. This is, of course, more general, right? Just random forest is highly nonlinear. Okay. But of course, it takes longer, right? Just all of evaluation in the easiest situation, I think just our evaluations, the random forest takes up more than 40%, 40 times of the computation time compared to our method when calculating those coefficients. And on the other hand, the NNL mixing gives you better interpretation because at the end of the least square model fitting, actually it turns out the only subset of the individual predicts will be used in the predictions. That is the overall, the structure, just which one contribute more in the situation and everything is more interpretable. Okay. And the NNL mixing admits the theoretical guarantees if you are using this model-based framework. And as I mentioned, so our theoretical results suggest that you do not really have to consider more complicated procedures, because at the end, the bias variance trade-off won't really buy you anything by using more complicated models. All right, so this is our evaluation. We want to evaluate these options in the 550 networks. The method, individual method, would be the method from their paper, and with 31 more model-based estimators again. And we won't really show the profit of single method because they are generally dominated by these in-sample learning methods. So here I just show the three options: the NNL mixing, the OLP, and also just without considering the non-negativity, we just directly fit the least square using the general linear combination. And here is something we got. Just the y-axis is the AUC on all of the individual networks, and we classify all of the results into the 6 domains. And here's the result. It tells you that, basically speaking, using the nonlinear mixing is giving you similar or slightly better results compared to OLP in all categories. But using the general linear combination is actually a bad idea. As I mentioned, it's just you suffer from this overfitting issue potentially. The random forest, because of the randomness part, it could handle that one better, right? But still, you don't really see the benefit of using the more complicated aggregation strategy. All right, so that is a high-level conclusion of the experiment. So at the end, we just show that just by using this non-negative linear combination, achieves similar performance to the LP. And generally speaking, we hope this could be an off-the-shelf method to model networks. It is general, reasonably fast, and almost tuning-free. Okay, and again, the implementation is available in the R package RedNet, available on CRAN. One limitation for this method, however, is by doing aggregation learning, you kind of lose some of the net structures, right? For example, if you have some individual model with community structures, but if you aggregate the one with some other models, then you no longer have that net structure. So that could be something we lose from the interpretation perspective. And if you want to achieve that one, maybe some post-processing is still needed. All right, any questions for this part? All right, so now let's switch the gear to the last topic. And again, I want to focus on the application motivation for this study. So here is a study from our biological collaborators. So essentially, they want to understand the colonization behavior and the association with genes. And specifically, they expose, the guppies into different environments, right, with different level of predators in their environment, and they want to study the behavior. And then after study, they actually identify about 600 genes. These are genes potentially controlling the colonization behavior of these guppies, and these will be the target genes for their study. Then they conduct additional experiments. They get additional data such that they now have the gene expressions, very large scale gene expressions, right? For each guppy, now they have about 60,000 regular genes also measured, right? These are the reference genes. And then they call some WGCA procedure to construct the gene network between the target genes and the gene network between the reference genes. So their high level question is, are the two networks different from each other? Right, between the network between the target genes and the network between the standard genes. And if they are different, how are they different? This would be the basic question we try to answer. And just for your information, this figure gives you the two networks there. Just very different. Of course, the reference gene is much bigger, with more than 16,000 genes, and the target network is just much smaller. And the first question, whether they're different, is trivial in some sense, right? Just because the two networks are very different in many aspects, right? They have different sizes. They come with different densities. The target genes is actually sparser in general. And, just a lot of differences. But these are not really, these are already known from their study, from their first wave study. What they really want to understand is, can we define the difference in a more useful and meaningful way for them? All right, so more generally, our problem is we need to characterize the difference between two unmatchable networks. When we say the two networks are matchable, because we cannot really match the individual nodes together. They are on completely two different gene sets, and they are from very different sizes. So scientifically, what would be a meaningful way to characterize the difference, and how to use a statistical analysis procedure to get the result would be our task. And specifically, actually, we want to introduce one more model that is actually not a parametric model. It's actually, as I mentioned, this is essentially the most general nonparametric model for exchangeable networks. We call it graphon model. We can ignore the details, but essentially we're assuming that there could be some underlying nonparametric function W that controls the generalization of all of the network. And we would write this procedure as this G, this network, it's generated from this rho n W, where rho n is a parameter we want to characterize the sparsity of the network. So this is just pretty general framework. And just without understanding just the full technical details, the high-level view for our analysis is, suppose we observe two networks. The first network comes from the first graphon function with some density scale. The second one comes from the second graphon function with another density scale, right? G1 and G2. What we really want to understand is whether these two latent unobserved functions are different or not, and how are they different. All right, and notice that even though we use notation, something different from the traditional, say, two-sample comparison situation in classical study is we actually only observe one data points from each model, right? We only have one network from model one network from model two. So there's nothing like, say, taking the average, doing some two-sample t-test, things like that just won't be available. Okay, so what we want to do is we want to use the so-called motive counts as our metrics. This is because the specific biological interpretation. Let R be a motive. A motive is usually a very small graph that could be a subgraph of your observed network, taking a specific shape. For example, a motive could be a V shape like this, or triangle, or 3-star. And then let X, this NR G, be the number of subgraph in G that is isomorphic to R. What we really want to compare is we calculate the subgraph count, the motive counts, and we want to compare whether they're different from these two networks in some sense. Okay, as I mentioned, we want to pick this one as our metric because of the nice interpretation. So a dominance of star shapes actually suggests a centralized system. On the other hand, dominance of triangles indicates a more transitive, a collaborative system of connections. And so that is actually the reason of doing this one. The drawback, however, is if you use a single network moment, just one graph, it is very, very limited and useful. Also, computationally, it could be very difficult to count all of the potential motives. So why are they limited and useful if you only use one? Because, say, if you want to use one specific shape of this 3-star, and then another specific shape as this V shape, notice that V shape is a subgraph of this 3-star, right? So if you have one network with a fewer number of this V shape, of course, you would also expect the network has a fewer number of 3-stars, right? Or a more natural example, say if you have a denser network, then you should have a higher count in all of type of subgraphs, in general. So it tells us that this is really because the individual difference of motives is not useful. If you test the difference, compare the networks by individual differences, you could generate a lot of false discoveries scientifically, just because they are essentially representing redundant information. So what we have to do is we have to incorporate the dependent structure between the network moments. So we could consider the higher order moments by taking the conditioning operation on the lower order moments. That means we have to do the test according to the conditional distribution. Therefore, let's assume we have k motif of interest, say R1 to Rk. Then our task is essentially to compare the joint or conditional distribution between this k different moments. All right, so how to do that? Well, notice that I mentioned that it is very difficult to compute them on large graphs. So what we have to do is we would apply this subsampling strategy. So starting from the original big network, we would randomly subsample a small number of nodes from it and take the induced subgraph. Let's call this G star B. And then we would calculate the corresponding motif counts on this subgraph. And we repeat this procedure, right? Just then we do this one run independently by another time. And we would have, at the end, m k-dimensional vectors. And then we would use this one as a random sample from the k-dimensional space as a null distribution for downstream inference. All right, so therefore, in this situation, we do not really handle calculating the moments on a size n graph. We only have to do it on size p graph. And theoretically, of course, our work is just showing that the whole procedure is actually correct. You are able to use this one to precisely characterize the distribution. But let's directly look at the result. If you directly compare the V-shape, it turns out the target network has a significantly lower value. And similarly, if you compare the 3-star, the target network is also giving you a lower value. However, notice that, again, because of their topological relation, so what really is meaningful is you need to compare the conditional distribution of the 3-star given the V-star, right? So we want to know that after accounting for the difference in the V-star, whether there's any difference. And if you're doing that one, this could be the corresponding distribution figure. And this is the target network. It just tells you that after accounting the difference in the V-star, the V-shape, you no longer observe any difference in the 3-star. So all of the information you observe in the marginal distribution is just purely redundant information from the V-star. And on the other hand, if we really compare the triangles, it turns out that the triangles gives very, very significant difference in the after accounting for the V-shape. So at the end, our conclusion is the target network has fewer V, but much more triangles. In the biological interpretation is that it turns out that the targeted genes tend to interact with each other in a more balanced and a transitive manner compared to standard genes, right? And that is really the biological insight from this analysis. All right, so just as a bonus example, recall that I mentioned the hiring network, right, between computer science departments. And actually, we also have another data set with the hiring network between the history departments. So let's just think about what could be the difference between these two different domains in hiring faculty members. And here is the result for the same inference procedure from the subsampling calculation. And in this figure, you can see that conditioning on the number of edges they have, you don't really observe any difference in their V-shape, right? However, if you really look at the V-star by conditioning the lower order moments, you can see that the history tend to give you a much higher value of 3-star. So the high-level conclusion is it turns out the hiring relations in history are more centralized compared to those in computer science. So just overall, people tend to hire in a more centralized version. All right, so that is really the subsampling method we want to introduce. I think I'm running out of time. And I want to thank all of the other contributors to the work. Ray Zhong Miao was my previous student at University of Virginia. He is currently the data scientist at Apple. Mingyu Qi is current UVA PhD student. Gan Lei is assistant professor at UC Davis. Wen Zhou, Colorado State University Stats and Public Health. And Kim Hawk is our biological collaborator at Colorado State University. All right, thank you very much for your attention.
All right, thank you so much, Tianxi. So any questions from the audience? Maybe let me throw in some thoughts first. So for the hiring relationship analysis, I feel it's very interesting because at least in computer science department, I think most computer science department nowadays are hiring very radically. That means they not necessarily hire from computer science departments. So
Yeah.
I think I don't know, how feasible, this analysis will, really
This is
push
fantastic question.
the
I mean, that's really motivating question. Yes, I agree. So first, this data set was actually I believe they collected this data set up to 2014. So this was about 10 years ago, right? So
I see.
definitely it did not really reflect, what we would expect in the current hiring market. On the
Yeah.
other hand, in this study, that was what they collected. They purely focus on computer science department, history department, say B school, things like that.
Mhm.
So definitely, I don't think that, at least for this data set, I don't think that there's much more we can do, because typically I don't think you would hire a lot of people from history.
Yeah.
But I think a better analysis would really just consider as maybe more of the STEM subjects together as a whole field. Then what could happen in a big network? I definitely believe that would be a very interesting question. I don't have the answer to that one, but if purely from the empirical study, right? See, even if you collect the data set like that, I believe it would be very helpful, impactful for the whole field of the complex system. I believe
Right.
impactful work.
Right. So yeah, another question is that, it seems like you are considering all these techniques mostly as some early processing step, right? For doing graph analysis, right? So I wonder, have you looked further into, for example, combine these techniques with things, fancy things like graph neural networks. I don't know whether you like this graph neural
There
networks.
is actually one going on project
I
about
see.
using GNN for as the improved analysis for the next step, but
I
that is
see.
still
I see.
at its early stage.
I
So
see.
yeah.
I see.
Yeah. But yeah,
Okay.
I think generally speaking, it's definitely is just only part of the analysis procedure. It's not really the complete flow chart at this moment.
Okay.
Whole
Okay.
pipeline still need
Okay.
more tools there. Yeah.
Okay. 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 All right. Any other questions? All right. It seems like people are happy with the talk. They understand everything. Okay. Uh, if not, then we are going to close the seminar. And thank you very much again, Tianxi. And
Yeah.
I really
Thank you
hope
very
to
much for the
see you in
invitation.
person. Yeah, I hope to see you in person on campus sometime.
Yeah.
Um,
Enjoy your trip.
yes. Thank you. All right. Thank you, everybody. Have a nice day. Bye bye.
Bye.